All right, we're going to work on pages 2 and 4 of our notes packet for linear approximation, 3.9 to 4.1. And so we're on example 3. Given that f of x is equal to the cube root of x, which I like to rewrite as x to the 1/3, in case I need to take the derivative of that, write the equation of the tangent line at x equals 27. So remember, this is often part of a free response. Anytime you're writing an equation for a line, you need a point and a slope. So start with the point. We need to evaluate f of 27, and cube root of 27 is equal to 3. So we've got a point, 27, 3. For the slope, I need to find the equation for f prime of x. This is where it was helpful to write this as x to the 1/3. So using my power rule, I get 1/3. X to the 1/3 minus 1 is negative 2/3. And so this is 1 over 3x to the 2/3. This pen, I'm sorry. Pen keeps cutting out here. There we go. And then remember, you need to evaluate the slope at this point of tangency. So f prime of 27 is equal to 1 over 3 times 27 to the 2/3. Now, with roots, remember, or I should say rational exponents, it's best to cube root first and then square. So root first, then exponent. This is 1 over 3 times 3 squared, which is 9, 1 over 27. And then remember, after you do all of that work, remember to actually write the equation. So the equation in point slope form is y minus 3 equals 1/27 times x minus 27. Use the equation of your tangent line to approximate f of 28. So f of 28 is approximately equal to 1/27 times 28 minus 27. And then I need to add this 3 to this right side of this equation. I can do a little bit of math here. You actually don't have to simplify on the non-calculator parts if you're doing free response. So this is 1/27 times 1 plus 3. I could leave it like that, 3 and 1/27. It is good to be able to do some of the math if they are giving us multiple choices where you need to put this together, but we can leave it like that. Use your calculator to find f of 28 and, to the accuracy allowed by your calculator. So let's switch over to Desmos. You could use your graphing calculator as well if you want to, but I'm focusing on Desmos because that's on our AP test. So remember, you can type in f of x equals, I'm not sure how to type in cube root. I would use the exponent, x to the 1/3. I would just use it as an exponent, but I'm sure there's a way to do it in here somewhere, but I like to keyboard as much as I can. So, all right, so what is f of 28? I'm going to write down to as many decimal places as this allows. So f of 28, according to this calculator, is 3.03658897188. Okay, and I'm just curious. Let's ask it what 3 plus 1/27 is. Okay, so we're accurate to 2 decimal places, and then by the time you get to the thousandths place, the approximation is different than the quote-unquote actual. Find f double prime when x equals 27 to explain why the approximation in part B overestimated f of 28. So why is 3 plus 1/27 bigger than actual f of 28? All right, so first find f double prime of x. Now remember, actually, let me start here. I'm going to write my f prime x equation and back in its exponent form. So it was 1/3 x to the negative 2/3. So to find the second derivative, I need to bring down this exponent. So 1/3 times negative 2/3 is negative 2/9. X to the negative 2/3 minus 1 or minus 3/3 is now minus 5/3. And then if I evaluate f double prime of 27, I get negative 2/9 times 27 to the negative 5/3. Actually, let me put this down here. Negative 2 over 9. I don't like to leave negative exponents when I'm plugging numbers in because I might forget that it's supposed to be in the denominator. Now, you can simplify this. This is negative 2 over 9 times, I'm just going to say 3 to the 5th. There's no reason to actually calculate this out because all we really want to look at is the sign, positive or negative, of the second derivative. So f double prime of 27 is less than 0. So f of x is concave down at x equals 27. And why do we care about that? I always do this sketch to remind myself what's happening. Some sort of concave down section, some sort of tangent graph. So the tangent line will be above, as you stray from that point of tangency, tangent line will be above whatever the actual value is. So because f of x is concave down, the tangent line approximation is greater than, I would write this out in words on the AP test, but is greater than the actual value of f of 20, or maybe at x equals 28. How about that? 28 is near 27. It's still concave down in that section. All right. This is from an old 2002 AP Calc test. So part B of this question said, write an equation of the line tangent to the graph of f at the point where x equals 1. Use this line to approximate the value f of 1.2, excuse me. Is this approximation greater or less than the actual value? So we can't find the actual value in this one, so we have to use this concavity idea. All right, so first things first, write an equation to the tangent line. So we need a point. The point would be at x equals 1, f of 1. And you can take that off the table. When there's an input of 1, f's output is negative 4. So we have the point 1, negative 4. We need a slope, which would be f prime of 1. When the input is 1, f prime is 5. So our tangent line equation is y plus 4 equals 5 times x minus 1. So that's the first part. That's done. Use this tangent line to approximate f of 1.2. F of 1.2 excuse me, is approximately equal to 5 times 1.2 minus 1. And then this plus 4 will get subtracted to this end. And again, we could leave it like this. I would like to simplify because it will simplify nicely. This is just 0.2. And 0.2 is just 1/5. So 5 times 1/5 minus 4. 1 minus 4, negative 3. So f of 1.2 is approximately equal to negative 3. That's our linear approximation. Is this approximation greater than or less than the actual value at 1.2? Now, I can't find f double prime, and I don't have f double prime in my equation. But what I do have is information about the table. So 1.2, let's look at what f prime is doing. From 1 to 1.5, where 1.2 falls within that, f prime of x goes from 5 to 7, and it's positive. I think that in this problem, we might have some more information about f prime of x. But I can see that f prime is positive, and I can see f of x is increasing. It's going from negative 4 to negative 1. So I'm going to say f prime of 1.2 is greater than 0. And I think I might justify this by saying because f prime of x is greater than 0 on the interval 1 to 1.5. Now, again, just with this information, that doesn't guarantee that f prime doesn't dip negative somewhere, but I bet there was something in the rest of this problem that we know that this stayed positive or something. So because f prime is greater than 0, f of x is concave up. Make sure you're being specific about all of this, by the way. You can't say it is concave up or the graph. You have to say what. So f of x is concave up. And I just do a little sketch here to remind myself, concave up means the approximation will be lower than whatever the actual value is. So the tangent line approximation will be less than the actual value f of 1.2. I could also, instead of writing the tangent line approximation, I could say f of 1.2 being about equal to 3, negative 3, is less than f of 1.2. All right, let f be a function where f of 1 equals 4, that's a point, 1, 4, such that for all points x, y on the graph of f, the slope is given by this. So now this is the f prime of x equation. Write the equation for the line tangent to the graph of f at x equals 1 and use it to approximate f of 1.2. So we already have a point. I still like to write that down for myself. It's kind of nice to get in the pattern of like always doing the same things for some of these problems so that you get these easy points. So I have a point. I need a slope. So I need to evaluate f prime of 1. And I'm going to do that by plugging in the ordered pair 1, 4 into this equation. So it's 3 times 1 squared plus 1 over 2 times 4, because when x is 1, y is 4. So this is what? 3 plus 1 is 4 over 8, which is 1/2. So my tangent line approximation is y minus 4 equals 1/2 times x minus 1. Use it to approximate f of 1.2. So f of 1.2 is approximately equal to 1/2 times 1.2 minus 1. Add this 4 over. Again, this is 1.2 minus 1 is 0.2, which is just 1/5, right? 2/10 is 1/5. So 1/2 times 1/5 will be 1/10 plus 4. So that's easy to just call 4.1. Again, not required to simplify. You could leave it like this. You could leave it like this. Whatever. Find the equation of the tangent line. They're calling it capital T of x to the graph of f at the indicated point. Use the linear approximation to complete the table. I don't like doing that, but I will. You're not going to have to do this, I should hope, on the AP test. Discuss the concavity of the curve based on your results. So what did it tell me to do? Find the equation of the tangent line. So we have a point. Let's find a slope. Remember, square root of x is x to the 1/2. So f prime of x is equal to 1/2 x to the negative 1/2, 1/2 minus 1. And let's rewrite that so that we get rid of our negative exponents. And then we can plug in the points, well, plug in the input 2. 1 over 2 times radical 2. So our equation for the tangent line, let's call it T of x. T of x is equal to f prime times x minus 2. I'm just going to add the radical 2 over here. You can still do y minus radical 2 equals this times x minus 2. I just changed it up like that because it'll be nice to have something ready to go to plug into my calculator. So, all right, let's go to Desmos here. I can set up a little table in Desmos. That might be kind of nice. Make things efficient. So we'll have the ability to set up a table on our AP test. So, all right, let's look at this. Oops. I just do. Our inputs are 1.9, 1.99, 2, 2.01, 2.1. And, how do I want to do this? Okay, so y1, let's make y1. You would type this in y and then shift hyphen 1. Or I'm sure there's a subscript somewhere in here in functions. Y1 is equal to, I don't know if this will work. Let's find out. Is equal to the square root of x1. Hey, there we go. Okay. And then let's add a y2. Let's call this y2. And y2, is this easier? Probably not. You don't have to do a table. You could do f of x and t of x and just like evaluate. Sorry, I'm just playing around with my table here. So what did we say this was? This was 1 over 2 root 2 times x 1 minus 2 plus root 2. All right, and then we could say, why can't I see this? Let me see if I can make this bigger. Bigger. There we go. So here are our two tables. Now, I'm not going to fill this out in the table on this video, but you can see we can do that. And then what was the question? Discuss the concavity of the curve. Okay, so let's take a look at our table. The actual values are a bit lower, it looks like, than the, right? Because we're matching, and then these are all just a little bit higher, it looks like. So the approximation is higher than the actual value. So I will write this into my answer here. So pretend I filled out that table. Wait, what's happening? There we go. Sorry. Pretend I filled out that table. So t of x is greater than f of x for all values in the table. Therefore, f of x is, so if the line is on top of the function, is concave down. I always have to sketch it. I can't just remember that for some reason. Is concave down at x equals 2. This doesn't mean the entire curve is concave down, just in this little area that we're looking at, concave down. All right, we filled out these notes in class, so I'm skipping to page 4. This is your other part of homework. So example number 3 says a particle moves along the y-axis. Its acceleration is a of t equals 15 radical t. So 15 t to the 1/2. Its velocity at time 0 is negative 80 feet per minute. So I'm going to make that v of 0 equals negative 80. Its position at time 0 is 0. So because we're on the y-axis, I'm going to call that y of 0 is equal to 0. Find the velocity function. So we are saying that the velocity function, v of t, is equal to, wait, have we talked about integration yet? I'm sorry. We're just figuring out how to go back and forth. Okay, sorry, I just didn't want to use my integral symbol. So I'm trying to figure out what would v of t be so that when I take the derivative, I get 15 t to the 1/2. So I kind of have to work backwards on this. I'm thinking, well, okay, what would I have to multiply? If I subtract 1 from the exponent to get 1/2, what would I have subtracted 1 from? 1.5, right? 3 over 2 minus 1 is 1 over 2. So that's that. And then this number up front needed to be something times 3 over 2 equals 15. Okay, so we can solve for that. Is that 10? If I put a 10 there, 10 times 3 over 2 is 30 over 2, which is 15, or 10 over 2 is 5 times 3 is 15. So yeah, so v of t must have been 10 times t to the 3/2. I will have an official rule for you that we will learn in chapter 4. It's just you're kind of trying to think around it right now. Okay, and then, oh wait, one more thing though. So we have this part of it. Now there might be a number here, like a constant here that we add or subtract, because remember, when you take the derivative of this, if this is a constant, well, it's just going to go to 0 for v prime. So what is this? Let's call it a plus c. What is this value? Well, remember, we were told that v of 0 has to equal negative 80. So actually, v of t has to equal 10 t to the 3/2, excuse me, and then we subtract 80 so that when we plug 0 into this, we get negative 80. So that's the velocity function. Find the position function. So the position function is the same idea. We're going to call it y of t. And I need to think, okay, well, what does y of t need to be so that y prime is equal to this 10 times t to the 3/2 minus 80. So if I take the derivative of that, what would I get? Okay, so let's start with the 80 part. if I had a minus 80t right here, then when I take the derivative of that, I get minus 80. So that part's done. Let's do the same exponent trick here. So what would t have had to have been? So you subtract 1 from the exponent, n minus 1 equals 1.5. It's just like add 1 to that is another way to think of it. If this was 5 over 2, when you subtract 2 over 2, you get 3 over 2. And then what would this number have to be so that this number times 5 halves comes out to 10? So some a value times 5 halves is supposed to come out to 10. All right, so 10 times 2 fifths. 10 over 5 is 2. 2 times 2 is 4. And then the last piece is the position. Now this just says, okay, yeah, y of 0 is 0. So the starting position when you plug in 0 was just 0. We don't have to write that down. So y of t is 4 times t to the 5 halves minus 80t. And I'm not going to write the plus 0 on the end. Find y of 8. Well, now that I have a y function, that's easy. It's 4 times 8 to the 5 halves. That's not going to simplify nicely if I root first, if I do square root of 8 first. But I also don't have to simplify it. I'm just going to say, oh, it's this, and call it a day. So that's my answer. You lose points on the AP test if you simplify incorrectly, and you're not required to simplify. So there's no reason to. Over the interval from 0 to 8, find the minimum and maximum positions. So what's going on from 0 to 8? Now, this is assuming you don't have a graphing calculator, because if you did, or Desmos or whatever, if you did, you would just graph y of t, look at it on this window, and see what's happening. So instead, what we want to do is look at the velocity, and when does the velocity change from positive to negative, whatever. So let's look at when v of t is equal to 0, or undefined, but it's just going to be 0. So when is 10 t to the 3 halves minus 80 equal to 0? So let's add 80 and then divide by 10. And then to get rid of the 3 halves, we raise both sides to the reciprocal power, 2/3. So the time is equal to the cube root of 8 is 2. 2 squared is 4. Okay, and then we put 4 on our little velocity graph here to test out signs. So if you plug in something like 0 into v of t, you get negative 80. This is negative. And then if you plug in something like 5, now 4 gets you exactly 80 out of this. So 5 is going to be something higher than 80. So it's going to be positive. Something positive, something bigger than 80 minus 80. So that'll be positive. So that means that y of t is changing from decreasing to increasing. So there is a relative minimum at 4. Now, it just says minimum and maximum positions. So there is no relative max. The only possibilities by the extreme value theorem, this is called the extreme value theorem. You don't have to label it, but you just show a little table and plug these values in. So our possibilities for the absolute or global min and max would be the endpoints, 0, any relative extrema that we have, 4, and the other endpoint was 8. So what is y of 0? We already know that's 0. What's y of 4? It's 4 times, 4 to the 5 halves minus 80 times 4. So what is this? This is 2 to the 5th. So this is 4 times 32 minus 8 times 4 is 32 times this extra 10. $128 minus 320. So this is less than 0. I'm not going to worry about how negative it is unless 8 is negative as well. And then what is y of 8? We already found that. Oh, we already found that, but we do need to do a bit of work on that. Okay, so how do we figure out that value? Because I have more room up here, let me do this. So this is where it's like, you don't have to simplify this unless it's helpful to simplify it. So let's change 8 because it doesn't square root nicely. Let's change it to 2 to the 3rd to the 5 halves minus 80 times 8. So this becomes 2 to the 15 halves minus, let's see, 8 times 8 is 64 times this 10. And then what is this working out to be? So how many times does 2 go into 15? So it's 4 times 2 to the 7th. And then there will be an extra radical 2 under there. And let's see, what is 2 to the 7th? 2 to the 5th was 32. 2 to the 6th is 64. So 2 to the 7th is 128. Okay, and I am getting into, so this is even more negative, I believe. Well, but it's minus 640. Okay, I'm at a point where I'm going to use a calculator because checking these numbers, comparing these numbers is not going to be nice and quick and easy. And to be honest, they would have something more clearly positive or negative. If we had, now I don't think we can call this y of t. Let's find out. If this were a no calculator problem, sorry, I stopped talking. If this were a no calculator problem, I think that we would have something a bit nicer to work with. Oh, this does work. You can call it y of t. Okay, so we want y of 0. Obviously, we are, what? Okay, instead of y, let's call this f. F of 0. F of 4. F of 8. Okay, so f of 8 turned out to be positive. Good to know. I was saying it was negative, so that's bad on my part. So what is the absolute max and absolute min? So the min is negative 192, and the max is this value here. So I'm going to write those down. If I want, excuse me, the absolute or the exact value, I could just plug in, like show y of 8. But I'm going to say min equals negative 192 at x equals 4. Max equals 84.077, I'm rounding that, about equal to, at x equals 8. Okay. Oh, also, what if they just asked me where the x values were? Would I had to have gone through all of that? The answer is no. So if I only had to find the x coordinate of the min and max, when I establish that v of t goes from negative to positive, and then it's not returning again, like there's not another 0, so it's not going to come back down to negative, you can say that you know for sure the minimum is at 4 because y of t starts at 0 and then it just decreases for a while. And then because it only increases after that, you know that one of the maximums has to be at one of the endpoints. But you still would need to figure out, is the endpoint at 8 greater than or less than the endpoint at 0? So I guess maybe you would need a little bit of a calculator for the max. Find the change in position from t equals 0 to t equals 8. So we have a position function. So this just means change in position is just what's y of 8 minus y of 0. So y of 8 minus y of 0 is really just equal to y of 8. So I'm not going to simplify, because remember y of 0 was 0. So I'm not going to simplify this. It was this 84 number, but I'm just going to leave it like this. That's the change in position. Find the total distance traveled. So from 0 to 8. So now that we know that from 0 to 4, y of t is decreasing, we would just need to say, okay, from 0 to 4, instead of doing, we can think of this two ways. Instead of saying y of 0 minus y of 4, we can just sort of like put an absolute value around that or subtract it the other way. But we know that if we're going from 0 to, what was this, negative 192, that's 192, a distance of 192. And then we're adding to that y of 8 minus y of 4. So I don't want to do this math in my head. So y of 8 minus, I don't have my screen flipped around. Oh, come on. Okay, fine. Flip my screen around. Minus 192. So negative 107. Oh, wait a minute. Minus negative. Sorry. Minus negative 192. There we go. I knew it couldn't be negative. So that's a distance of 276.077 because that was f of 8 minus f of 4. F of 4 is negative. So plus 276 point, too many windows open, 0.077. I'm leaving that on my screen, and I'm taking that value and I am adding another 192. So total distance traveled is this distance that it decreased plus the distance that it increased, which is a total of 368.077. All right, that finishes this homework assignment, which was just sort of finishing our examples and our notes. Please come into office hours or see me during Flex if you want to go over any of this.